Chapter 5, Trees. Trees are really popular data structures, especially when the data can be represented as a hierarchical structure. And the trees are really efficient data structures, especially when we search for some things, we can come up with the trees. And we will start this chapter with some instruction about trees. And then I will talk about binary trees and heaps and binary search trees. All these topics are really important. Okay, what is a tree in the data structures? So this is quite similar to the trees in nature. Okay, that's why we call it tree. And in the data structure, we have root and branch and leaf. So we share the terminologies, but they are slightly different. And what is a tree in the data structures? Okay, tree is a data structure representing hierarchical nature of a structure in a graphical form, like this graph. Okay, so one book can be represented by a tree. Okay, so book has lots of chapters, and each chapter has sections, and each section has subsections. Okay, so this is a tree. Okay, as I said in the previous slide, a tree is a kind of a graph. Okay, so when we study a graph or graph theory, then one tip is that we have to stick to the definition of the terminologies. Okay, so let's take a look at some terminologies of a tree. So tree is a set of linked nodes, and as you can see in this graph, the one node has two or one links or pointers. Okay, so this is connected to the chapter 4 in a sense. So it is a set of linked nodes, and each node has a 0 or more child nodes. Okay, so in general, we can have many children. Sometimes we have some constraint like at most we can have 2 children, then that's binary tree. We'll talk about that later, but in general we can have many children. Okay, or we can have just the 0. So 0 or more child nodes, and which are below it. Okay, so usually the children are below the parent. Okay, and a node has at most one parent. Okay, this is important to think too. At most one parent. We cannot have 2 parents. So in these examples, the node 6 has one parent, which is 7, but 6 cannot have 5 as a parent at the same time. Okay, so by this constraint, tree is not making a loop. Okay, and a node without a parent is called root. So in this graph, 2 is a root node, and a node with no children is called the leaf. So 2. Okay, so we have a two nodes. Okay, so at the bottom of this graph we have 5, 11, 4, and in the middle of this graph we have a 2. So these 2, 5, 11, 4, they are leaf nodes because they don't have children. Or we can define a tree recursively. Okay, so here is a recursive definition of tree, which is a finite set of one or more nodes such that there is a specially designated node root. Okay, so we have one node, and remaining nodes are partitioned into a positive n disjoint set t sub 1 and to t sub n, where each of them is a tree or subtree. So look at this graph. We have one root node A, and it has some subtrees. Okay, so in this example we have 3 subtrees. Okay, and then in the subtree, let's zoom in. So let's focus on T1. Okay, in the T1 is a subtree, which means the T1 is also a tree. Okay, so and then in T1 we have one root node which is B, and then we have subtrees. EKL makes one subtree, and F is another subtree. Okay, and then one step further, in the subtree of T1, so the first subtree is EKL, right? In this subtree, E is the root node, and K is one subtree, and L is another subtree. And then when the k is the subtree, then the k is a root node in the subtree, okay? And then we have zero subset. We have zero subtrees. So that's it. So we can define a tree in a recursive way. And as I said, the definition of the terminologies are really important to avoid unnecessary confusing in the algorithms. Okay, so we have lots of terminologies in this slide and the next slide. So the first one is degree of a node, which is the number of subtrees of a node. Okay, so we have an example tree on the bottom of this slide, and degree of A is 3 because we have a B, C, D. So we have 3 subtrees. And degree of C, node C, is 1 because we have only one subtree, G. And the degree of F is 0 because F doesn't have any subtree. Okay, and the degree of a tree is the maximum degree of the node in the tree. Okay, so in this tree, degree of A is 3 and degree of D is 3, and that's it. We don't have any node with degree 4. Okay, and next one is a leaf node or terminal node, which is a node with 0 degree. So in this graph, K, L, F, G, M, R, J are leaf nodes. And the roots of the subtrees of node X are the children of X, and X is the parent of its children. Okay, so in this graph, B is the parent of E and F. Okay, and then E and F are children of B. Okay, so to B, EKL is one subtree and F is one subtree, and E is the root node of the first subtree and F is the root node of the second subtree. Okay, so that E, F are children of B and B is the parent of E and F. Okay, the sibling. Sibling is the children of the same parent. So H, I, J are sibling. Okay, and G and H are not siblings. Okay. And path is a sequence of nodes in which each node is adjacent to the next node. So from A to L, we can find one path. So since one node has only one parent, and there is only one path between two nodes, okay? And ancestors are all nodes along the path from root to the node. So let's say our node is L. Then from root node, which is A, to L, we have A, B, E. Okay, so these are the ancestors of L. Okay, and descendants are all nodes that are in subtrees. So to A, all the other nodes are descendants. Okay, and to B, E, F, K, L are descendants. And level of node. So letting the root be at level 1, okay, then if a node is at level I, then its children are at level I plus 1. So A is at level 1, okay, then the B is at level 2, and the E is at level 3, and the K is at level 4. Okay, and then the height or depth of a tree is the maximal level of any node in the tree. So this example tree, the depth of this example tree is 4 because the K is at level 4. Okay, if we follow this ACG path, then we have just this subtree depth is only 3, but by definitions we need the maximal level of any node in the tree to get the height, which is 4 in this figure. There are a couple of different representations for trees. Okay, so the first one is the conventional representation. Okay, in this conventional representation, we use a graph. Okay, literally. Okay, and then the Venn diagram can be alternative choice. Okay, and then list representation is another choice, and the table is another one. Okay, so the conventional representation is easy to understand. Look at the Venn diagram. So we have one circle with A and the subtrees. And in the subtree, we can define this Venn diagram recursively. So in the first circle we have A and subtrees, and in the subtrees we have B and the D, E, and another circle, and then we have C and F and G, right, to have the subtrees. Or we can use the list representation with the parentheses, something like equations. Okay, so do you remember when we talk about the expressions, we use the tree to represent the expressions? Likewise, we can use something like expressions to represent a tree. So we have A, B, C, D. We have the nodes with the parentheses. So basically, these parentheses can represent a tree. Or we can use tables, like a table of a book or papers. Okay. In the previous slide, we talked about a couple of different alternatives to represent a tree. Then let's think about how to actually implement their representations. So what kind of data types are useful? Okay. So first, we can come up with an array, a 2D array. Okay. So as you can see in this slide, each row has a data and the k links. Let's assume that the degree of this tree is k. So at most we can have k children. Okay. Then we have a data value for one node and we can have k links. Okay. So for example, if the root node has 3 children, and when the degree of tree is 3, then this link 1, 2, 3 will point to the index of the children. Okay, so if we have 7 nodes in the tree, then we have 7 rows, and if the degree of tree is 3, then we have 3 columns for links. Okay, so the 2D array can represent one tree. Okay, so this is not the best way to represent a tree, because we have a varying number of fields. I mean, each node can have 1 child or 2 children or 0 children. Okay, so we don't use all the links here. So as we've seen in the sparse matrix, we don't use lots of links in this 2D array. Then let's just calculate how many links actually we use. Okay, how many links we are actually using here, or how many links are not used. So basically, we have n times k links in this representation. See that? If we have n nodes, then we have n rows in this 2D matrix. Okay, and then we have k links for each node. So we have n times k links. Okay, then how many links do we use actually, given n nodes? Actually, we use n-1 links. How do you know that? Okay, just look at this one figure. Okay, the left side of this slide, we have one example, a tree. Okay, so look at this figure carefully. Then each node has one parent. Okay, so each node has one parent except the root node. And all the edges are counted by the nodes except one root node. Okay, so the edge between A and B can be counted by node B, and edge between B and E can be counted by node E, and edge between E and K can be counted by node K. So when we have n nodes, we have n minus 1 edges. Okay, so then we need n minus 1 links. That's enough. But in this representation, in this 2D representation, we have n times k links. So out of n times k nodes, we use just n minus 1 links. Out of n times k links, we use just n minus 1 links. It means n times k minus n minus 1 links are just the zeros. We don't use that. So that's how we get this n times k minus 1 plus 1 links are zeros. Okay. Okay, this number is coming from, from that we have n times k links, but we use only n minus 1 links. Okay, look at this figure really carefully, then you can figure out how we get this number. Okay, and then next issue, the left child, right sibling representations. So given this one example on the left side, so A has 3 children, okay, B has 2, and C has 1, and D has 3, okay. So if we have k children, then that's not easy to represent one node with a structure. So think about the structure in the linked list, okay? Then we used one data field and we had just 1 pointer. But if we have 3 children, then we need 3 pointers. If we have 4, then we need 4 pointers. So depending on the degree of this tree, then we have to have that many pointers, okay? So that's not that beautiful, okay? If we change the topology of this tree, then we have to actually change the structure, the definition of the structure, okay? Instead of changing the definition of the structure, okay, depending on the degree of the tree, why don't we just change the topology of this tree? So instead of having this regular tree, we can just transform this tree into right sibling representations. Okay, so then A was a root node, and B, C, D were a sibling in the left tree. But now in the right tree, B, C, D is connected because they are siblings. And then in the next level, E, F is connected, and then in the next, K, L is connected. Okay, but F and G are not connected because they are not siblings. So G is connected to C. Okay, and then H, I, J is connected, and H is connected to D. So likewise, we can transform any kind of trees with any degree to this right sibling representations. And then in this right sibling representations, each node has 2 children at most. So now we can define our structure with 2 pointers. Okay, so left child and right sibling. Okay, that's how we can define our structure. And let's assume that we have a degree 2 tree, then that can be represented simply. Okay, each node has pointers to left child and right child. Okay, and actually from the previous slide, right child, we use right child instead of the right sibling. Okay, so we assume that now our tree is binary. So binary means each node can have 2 children at most. So given a general tree with the degree k, then we can transform this tree into the right sibling tree. And anyway, now let's assume that we have a binary tree. Okay, then each node can be represented by a simple structure where we have a data field and we have 2 pointers. That's it.